we're ready to start section 4.9, which is on something called antiderivatives. So I need to define what an antiderivative is. So we begin with a definition. A function capital F of x is an antiderivative of a function that I'm going to write as little f of x, okay, on an interval I. Now notice I'm not specifying whether it's a closed interval, which would include the endpoints, or an open interval, which would not. And I'm not specifying whether the interval is finite or infinite. So it can be any interval. It could be negative infinity to infinity if both functions are defined there. It could be a very finite interval, like from 0 to 1, including or not including the endpoints. Okay. So big F is an antiderivative of little f on the interval I if f prime of x is equal to f of x on that interval. Okay. So we've been starting with a function and calculating the derivative. Now we're going to be going in the opposite direction. We're going to start with little f, and we're going to try to find a function big F so that when I take the derivative of big F, it gives me my original function. Okay. One important thing in this definition, that says an. It does not say the. So if I have a function, I can ask you to take the derivative. Every function that's differentiable has one and only one derivative. However, if a function has an antiderivative, it has lots of them. They're not unique. Okay. So let's just start with an example. Let's suppose little f of x is x squared. No, I didn't even want to start with that. I wanted to start with a simpler one. I wanted to start with 2x. Little f of x is 2x. And I want to rack my brains. I sort of gave it away here. I want to rack my brains and see if I can think of a function whose derivative is 2x. We've seen that. X squared works. So I could say f of x equals x squared, and I can check. I would just take the derivative. Yep, when I take the derivative, I get 2x. Okay. So now I want to see if I can think of another function whose derivative is 2x. And we don't want to actually get too creative here, because if we get too creative, we're not going to get a correct answer. I want to think back to section 4.2. In section 4.2, we had something called the constant difference theorem. And that said, if f prime of x equals g prime of x, I'm just going to use capital letters here because I'm thinking of them as antiderivatives, on some interval I, then the difference between f and g, so f of x minus g of x, is c for some constant c. Okay, so if two functions, f and g, have the same derivative, then they just differ by a constant. Notice this would mean that f of x is equal to g of x plus that constant. Or equivalently, g of x is f of x minus that constant. And of course, since the constant is arbitrary, it could be a positive or a negative number. Okay. So if I want to think of another function that has the same derivative as this, I now know what I need to do is just add a constant to this. So I could say g of x is x squared plus 5. Well, there's another function that has the same derivative of 2x. Okay. And notice, if I wanted to check, g prime of x would just be 2x plus 0. Adding a constant doesn't change the derivative, because when I take the derivative of a constant, I just get 0. Okay. So we can sort of summarize this. There's a theorem that we have in this section. It's called Theorem 1. If f of x is an antiderivative of little f of x on some interval I, the most general antiderivative is f of x plus c, where c is an arbitrary constant. Okay. All right. So I'm going to introduce some notation. And this is notation that the book will introduce eventually. The book doesn't actually introduce this notation until chapter 5, but it's going to make it easier to talk about these things because it's the notation for the general antiderivative. Okay. So here's what we have. The integral of f of x dx. This S-looking thing is an integral sign. Okay. And what I've introduced here, this and this is really one symbol. This says it's the integral with respect to x. And this is the thing we're taking the integral of. Now we have seen that this has some meaning by itself. Very important to recognize this does not. Okay. So if you write that without the dx, you're writing nonsense. Okay. And it's going to feel tedious for a while that you're writing these dx because we're always going to be integrating with respect to x. Although sometimes our variable might be t and then we'd be integrating with respect to t. Okay. It actually does become really, really important. So a lot of students at this point in their math career develop the bad habit of not writing that differential. I am warning you, do not start that habit. Breaking it is much harder than not forming it in the first place. These two pieces go together. Okay. And what this means, this is the general antiderivative of f of x. It's also called the indefinite integral. So that's just some new vocabulary. Indefinite integral of f of x. It means the general antiderivative. Okay. So integral is a new word. You might be wondering, why is this indefinite? Is there such a thing as a definite integral? And the answer is yes. And we'll be seeing what a definite integral looks like in chapter 5. Okay. So this gives me, as I said, the general antiderivative. If I wanted to take the general antiderivative of of 2x, we've just seen it would be x squared plus c. Notice it's not just a single function, it's an entire family of functions. Geometrically, what that plus c does is it takes that x squared, which is just a parabola, and it takes vertical transformations of that. So if I take a graph that has a certain derivative that describes its behavior, I can translate that up or down without changing the derivative at all, is essentially what the constant difference theorem tells us. Okay, so that's what a general antiderivative is. That's the notation that we will be using. And throughout this section, we're just going to be developing a bunch of formulas for doing this going backwards from here's the derivative, what function did I start with? In other words, taking the indefinite integral or finding the general antiderivative.